Doctor,
Yeah.
can you share the QR again just now? Because I forgot to scan. Okay, thank you, Doctor.
Okay. Fine. Yes. Assalamualaikum. Afternoon. We have any question for yesterday class? Please ask. So today cover gas. So for the gas cascade analysis is based on the paper by Professor Dominic Fu. The title of the paper is setting the minimum frequency gas flow rate target using cascade analysis technique. In the paper, there are four examples. We start from the simplest one, nitrogen integration. The typical process integration technique for resource preservation comprises two steps: setting the minimum resource target, followed by design of the resource preservation network to achieve the minimum resource targets. Generic operating technique applicable for various types of resources. Resource conservation network include graphic planning for deposit curve, or numerical targeting techniques. Recent numerical targeting methods such as cascade analysis technique has been proven applicable to what the previous step. The two key, this is based on the paper. Two key difference between surface problem of water. So until now, we have learned about water cascade analysis. First, different between water and gas analysis. While pure freshwater feed with zero contaminant has always been assumed to be available for synthesis of water network, it is quite common to encounter impure fresh feed for the gas network. Second, water network may consist of a mix of mass transfer-based and non-mass transfer-based processes. Hence, the flow rate for water feeds may not be fixed. However, this is not the case for the gas network to maintain steady state operation. To maintain the system pressure in a gas phase hydrotreating reactor, it is necessary to maintain a uniform inlet mass flow rate and gas concentration for gas consuming process. So the first one, uh, we cannot assume zero contaminant load for the fresh water, sorry, for the fresh feed related into previous network. The second one is for the gas network, uh, the inlet mass flow rate is uniform compared to the water network. It's varied. Example one, big one shows the process flow diagram of a magnetic tape manufacturing process. If you refer to paper 4, first picture. So figure 1, this is figure 1, shows the process flow diagram of a magnetic tape manufacturing process. Coating reagent are dissolved in an organic solvent and form a slurry mixture. Even binder. The slurry is then suspended in resin binder and special additive. Next, the coating slurry is deposited on the base film. Nitrogen, okay, this is where the nitrogen is used. Nitrogen gas is used to induce evaporation rate of solvent that is proper for deposition. A small amount of the solvent is decomposed into other organic species in the coating chamber. The decomposed organics are then separated from the coating chamber exhaust gas using a membrane unit. Coating membrane. The retented stream consisting mainly of nitrogen gas and laden with 1.9 to 1.9 weight% organic solvent. Lift the membrane at a fluid of 3 kg per second. The coated film undergoes a drying process here, where the nitrogen gas is used to evaporate the remaining solvent. So here is the nitrogen, another one nitrogen inlet. So it didn't specify what is the concentration for the nitrogen. The coated film, okay, The dry exhaust gas has a point of 5.5 kg per second and a solvent concentration of 0.4 wet over wet percent. The two exhaust gas streams are mixed here, and this also goes in the ignition. To reduce nitrogen consumption, it is proposed to reuse and or recycle the solvent-laden exhaust to the coating and drying process. So instead of goes to the yes the waste, we use or recycle back for the coating and the drying, but they are constrained. So for the coating, the flow rate of gaseous speed is between T to 3.2. Solvent concentration is between 0 to 0.2. Drying is 5.5. Flow rate of gaseous speed in 5 to 6. Between 0 and 1. The outer condition for the coating and drying process are assumed to be independent of the feed gas concentration. The constraint listed above require the gaseous flow rate and its solvent concentration and unit to fall within the given range. So two key strategies to maximize the reuse and the recycle, since we want to reuse back the gaseous emission. First, the maximum permissible limit, permissible concentration should be assigned as the limiting concentration, while the minimum feed flow rate should be assigned as the limiting flow rate for each processing. Second, the cell source should be segregated into individual streams, since mixing tend to degrade the source stream quality. For this example, the stream-laden exhaust gas should be segregated into membrane-retented and drier exhaust gas. A fresh makeup hydrogen is solvent-free and hence has a limiting concentration of 0 wet percent. Okay, so the fresh nitrogen is 0 wet percent. This is based on the paper. Oh, no. Meaning that in the inlet for nitrogen here, 0 with the highest point. The limiting data for gassing and source step level 1. So the sink here refers to demand as well. The source is the process, sink or demand is the process. Okay, that's done. 4, 25. You are the okay. This makeup area is 7 3 is a limiting version of 018 the same. But based on this limiting data, the inlet for drying and for things that pure point 1 and point 2 stated. say special water supply. If you refer, so the cascade principle for this study is the same as water. This is based on which figure 2, page 3 in the paper. So in cascade principle, it's conceptually explained in figure 2. In figure 2a, this figure second of this is a gas source. And a pretty concentration of 5%. On the other hand, gassing is just G per second. And the setup and pretty concentration of 10%. Just considering reuse 50 kg per second of waste gas have to be purged. Figure 2a certificate. Again, gassing exists at 10 kg per second, and except up to an pretty concentration of 10%. Without considering reuse 50 kg of waste gas, this is for the first case scenario. We have to be purged while 100 kg chicken will have to be supplied to satisfy the sink. It's similar idea to water. So if we with the nitrogen cascading, so meaning we reuse or recycle. So by making use of 50 kg per second of the gases as seen to satisfy the gassing that can generate a higher quality of the machine is referred to avoid purging the gas source directly as emission. So since the tolerance is less than 10%, and the incoming feed 5%, which is within the tolerance limits, so we can just direct the 50 kg per second to this process, and thus reduce the amount of feed by percent. And there are no waste gas generated. So the principle is the same as water. The two things that is different. Cascade analysis GCA technique. Okay. So first step in correcting GCA is to locate the various gassing and source of their respective concentration level. The one already being summarized in table 1. The gassing. Pay attention to the concentration. In this case, it's straightforward. There's no overlap between sink and source. Shown in table 2, solution level CK, arranging in ascending order, and the flow rate of each gassing source is located individually at its respective concentration level K in column 3 and 4. So from the table 1, arrange it in ascending order from 0 to 100 to 100 equal to the maximum 0 for the fresh water supply. Different compared to water. Because in water we use ppm. So if you use ppm, then the maximum is 1 million here. Now that we use weight percent as a unit concentration, this is 100%. Grade 5.5 and 3 is from table 1. Substitution 6. Source 1%. So Fi minus source minus C. Yeah? This is Fi. Fi. This is C. So pay attention. This one is source minus C. So say source minus C. So automatically 0 minus 5.5 is impedance square. Yes. So the next step, the next GCS step is the cascade the net flow rate so plus to visit down the stream level to yield the fluidity. Okay, for the FC, okay, it's FC. So for the FC, it's cascading similar to what the flow rate is cascading. Yes, it's similar. So it's similar to the cascade as well. The cumulative water source demand, we do cascading. So method wise the same. So for the first gas cascade level, start with speed of 0. Okay, 0 is minute. No, not with audio. That's sure. That's it. Gas tension. Water, yes. Yes, definitely. To start with FC here refer to fresh feed. Mm. Mm. Yes, this is a fresh feed. This is the discharge flow rate, fresh flow rate. So since we start with zero, the fresh discharge is zero. We have a line. So we do the cascading. 0, 5.5, 5 plus negative 3, 5 plus 1.5, 3, so on. Next, column, column 7. Column 7. So the column 7, table 2, is the let's see, okay. Oh, that's the same. See, private delta P. So then try this. So please check it. The, uh, the pretty load delta M is in column 7. 2 is obtained from the product of cumulative exponent FC. Extension into such given delta C. So if you still remember yesterday for the water, it's delta P. Yeah, not pressure, it's purity. In this case, it's delta C pressure. So since the concentration is in weight percent, we divide by 100. Then we get 0.001 divided by 5.5. This is interval between this 0.1 and 0.3. Then you get negative 0.006. Oh, what 0.4 to 0.5. What? So, it's a lot. C. 0.1. So how to do it? 0.4 minus 0.2 divided by 100 multiplied by 8.5. We get 0.017. And creativity load. Cascading temperature load down regulation level 8. Infinitely collecting the flow rate of fresh gas needed at discussion level or the level fresh gas flow rate SFK. So for the cum delta M here, cumulative load. This is based on cascading resolution here. So this is between the interval of these two daily. Go down and get 0 plus increase. Okay. The largest negative FFK which actually represent the minimum fresh gas flow rate cascaded down the within the minimum discharge flow rate. So it's similar to method with water cascade analysis. So what happened here is identify the largest the highest negative value as the minimum discharge flow rate. If you still remember for water, we will call it minimum water target, minimum water target. Yes, is minimum discharge flow rate. Note that the impurity load delta M shown in column 7, table 2 is obtained from the product of cumulative gas flow rate FC the cascading the not okay. So referring to table 2, this is infeasible gas cascade table since the cumulative delta M here is all negative. Just mean that there is insufficient utility gas at the respective concentration level. The amount of interval gas flow rate FFK is obtained by dividing cumulative delta M by the difference between the concentration at level K fresh feed concentration. Fresh feed concentration. So, try this. One, two. Okay, so we use this equation monotable fresh gas solid aggregate to divide the two special concentration. This not sure what is the special concentration since this is gas. We cannot just assume it's zero. If you refer to table one, even guessing it's not zero, 0.1, 0.2, meaning the nitrogen is not there. Your not sure what happened, but it seems like the concentration is actually not accurate. This, yeah, if you use the method, it's 0.006 divided by CK here, CK intersection level 2 minus CF in this case, with the description. The fresh makeup nitrogen is 0%. So 0.2 minus 0, 3. How about 0.003? Back to 7.5. 6. Then we let it go. Divide all calories. The based on this, actually the value is 0.21, but make it shorter 0.2. That's why if you use 0.2, here 0.3. But the method is correct. 6. So this vision. TK is 2. 0. This is with setting. This is with set of sets. Right. Good. Get to go with and set the time. If you use your calculator, you will get -3. Why? Because 0.2 is not accurate. It should be 0.0. So right. The actual value for this is what? Satu lapan. This one should be 0. This is the accurate value based on the 2.7 0.006. Since the author, they just bunda to the nearest integer. So yeah, that's why it's not telling. But the method is how CF is 0. How do you know the CF is 0? Go back to the condition. Yeah. For the cutting, it's start with 0, right as well. The highest is 1. Okay, continue. The absolute value of the largest negative FFK is 5.625. This value, 5.625, is actually the minimum cash flow rate target FF. So, refer back to the method. We start with 0. Next is we use the largest negative value to be the fit. Then we do again the calculation. Starting from here lah, FC. We do the cascading. 5.625. That's 5.5. 0.125, and so on. So this is the discharge of the gas is the same. That's for the discharge. 5.625. Delta M. So delta M is calculated by FC by delta C. the cross concentration level. Okay. How to calculate this? This one with one. Okay. 21. 100. 0.00560. If you so if you round it to the nearest integer like this, at the end the answer is that accurate. Then we do the rest and we find that negative 5.65 the same concentration level K, sorry, concentration level 4. Oops. It's zero because of the pinch. This is concentration of the pinch. This is the pinch. So based on this, the fit required is 5.625. Refer back to table 1. Without the cascade analysis, the amount of nitrogen needed is 8.5. Now it's reduced to 5.6, which is 54% reduction. Oh, video. This amount, this amount is shaded down the FC, visible GCP cascade table. Nitrogen discharge fluid of 5.6. Okay. This concentration for the gas network is 6.4%. 6.4%, there is a zero. Um, from the meeting data in table 1, emission from the drying process is 2, source 2 drying classified as pinch causing for this example. SR2 5.5, okay. Drying outlet pinch. Sources. Achieve the minimum gas target to prevent 75 kg per second of SR2, which raises the interval K and 3 should be elevated to the region of the pinch. While 2.65 K4 and K5 should be below the pinch. Okay. The exact pinch causing extreme restriction to meet the source target. Okay. Okay. So that is for the nitrogen. This is for the oxygen. Still in gas cascade analysis. Let's explain it. Figure 4, isn't it? Figure 4. Oh, 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 it's they combine it well. So for the, because once you come up with the pinch, then you need to come up with a new process flow. Oh, the other. Oh, oh, letters. All right, and then we go for the second example. Any question and ask? Take a break first. Oh, 10 minutes. We will continue another two example, including hydrogen integration. Okay, back, continue. Subject integration. Some variable on oxygen integration is focused on the optimum reuse oxygen operation plan. The following case study is an attempt to explore the interaction and possible satellite integration between process and the section for the human oxygen recovery. Figure 3 show a process land and consume a large amount of high purity oxygen. Oxidation process. A relatively small portion of oxygen is fed to the end to enhance the combustion system. As well as for the aerobic section of the Westbrook electrical plant, The source of oxygen emitted from the oxygen consuming process is still unknown. It should therefore be reused or recycled to reduce the free fresh oxygen take. Limiting data for all oxygen switch source are given in table 4. Noted since GCA is able to handle pure fresh with the 5% purity in fresh oxygen supply should not pose any problem in meeting accurate minimum gas product target. So for this case, the fresh oxygen supply is not pure, 5% impurities compared to the nitrogen in the first example, 0%. The GCT for this case study, level 5, if fresh oxygen supply FF and the discharge target for say in this group. This corresponds to a fresh oxygen consumption of 27%, just gas consumption of 73%. The system shown in figure 2. Yeah, of the system. Exercise. Oh, it's okay. So for the exercise, we have pick the source. That's on figure 3. So there are two processes. Yes, this is the one. So process 1 to figure 3 or in the slide. Process 2 5. The same. We specify second percent thing. 10% also the combustion that to 65%. That's what the gives it 65 same BPs as well. So first thing you need to do is construct the BTP, gas cascade table. So the first column for your gas cascade, this is access for the exercise. The first column in your gas cascade table is the level. So in this case, how many level? It's 6 level. 6 level. How do you know? 1, as I said, 2, 27, 3, 7, 6, 7, 6. Next is then in ascending order range or sort the concentration in ascending order 10 or from 5 to 100%. So 100% is the maximum. Then specify the what is F G is thing. Specify the thing first. Formation of the thing. So in this case, for the thing, you have only two concentration, although there are four strips. Ultimately, only two. For the 10% and the 65%, just add it up. Then for the source, can source limited to 3 or 3, okay. Yeah. So 2, process 1 and process 2. For 10 and 5, we do the source minus sink. This another column. But for the first CT, yes, cascade table. You need to use. You need to start with fresh fit of 0. So from the fresh fit of 0, then we identify the minimum gas flow rate to satisfy the requirement for this process. In this case, once you define the pinch, then need to construct another table with the FF is based on the pinch. For this, based on the paper, the pinch is at X concentration level 3 or 30 kg per second. So meaning you do it with FF equal to 0 order feet fresh 0 per second. So the highest negative is 50. So for the GCT, is including WCA, water cascade table and gas cascade table, both require two table. Okay, I put it in edit the exercise which you need to do. Okay. So the minimum required fresh oxygen supply is 30 kg per second. If you compare to the unmodified process, so it require around 41 kg per second. Since we reduce it to 30, so the amount of fresh oxygen emission is around 37% with the discharge gas emission of 70%. So discharge is around 15, 10 plus 5, 15. Based on cascade table 4, which is network design. So this network design is for example 1 and example 2. The paper. This section briefly review the design techniques for the liquid gas network. Note that alternative technique for water network design may also be applied in combination with the fluoride tablet, which one established using the GCA technique. The pinch point concentration in the targeting stage play an important role in designing a network for maximum gas reuse or recycle. The pinch divides the network into two design region above the pinch and those below the pinch. For problem involving a single pinch, it is essential to observe the pinch division in order to achieve the minimum flow rate established during the targeting stage. In the region above the pinch, the cumulative impurity load surplus is less valent deficit and there is always excess in the region. The region above the pinch, above the pinch is for the overall gas flow rate of the following the above observation in designing a gas network, gas source above the pinch the supply must not be fed to aggressive. Below the pinch, violating this will result in higher fresh gas flow rate. This will gradually the same gas being from pinch region. The pinch project stream that exists at the pinch position is an intersection of this theory. We call it part of the pinch project stream below the region with the pinch. To maintain steady state operation of the gas exchange process, we need to maintain a uniform mass flow rate and concentration at the inlet stream of the gas exchange process. The following guidelines can be used to design the network. Flow rate Fij rate the source SRI is kg. Gas content. That one is for the same for the source flow rate is SRI. Okay. Same but F equal to FSR, which is the source. Question 2 and 3 are constraint or limit representing the flow rate replacement required by the signal. The question 4 states that flow rate of source tide and J limited by the ability of to any gas from a source that is not fed to a sink will move as discharge stream. The gas network, for example, 1 and 2, designed using the above formation is shown figure 4 and 5. Respectively, the flow rate target as well as the gas emission target for the bridge goes straight during the distillation here. Noted using this stage, the gas network should be designed only to each region. System of the gas was blown. Different design agents. One is about mixing. It's if one two 227 plus peringatan 75 subsequent 7 of tujuan grafik 1. Yeah. So 1.5, 1.375 is coming from the drying, checking the pinches. I know the pinch at drying nut. Oh. So at the pinch point 2.875 from kilograms. Okay. 2.875 coming from the 0.2 0.2 from the dry. Okay. So then if you add this up 1.375 and 5, it's a 2.7. That one is the point, is the stream above the pinch. is 2. This is the highest. Going from here. Check cos to things to and however, the requirement for the coating and the drying is not enough. So meaning we need to get up with the fresh nitrogen. Okay, so for dry is 5.5 for 1.5 plus 1.375. So it's equal to sum up is 5 to equal to the 5.5 required uh, by the dry as the seed white is for the cycle it was one. It's how to it's how to dry the liquid. This two one. This two one dry. This one is this two one. Two. And four. The concentration. This two is equal to table one. The source number two is one dry hydrogen. This is 0.4%. F2 once for the gas cycle. F is R. F is R1. R2 two is dry. R1 dry. Another one is dry. Two two is but valid. This one should be F2 this F21 because this is the source is from dry. It's R2 supplied to SQ2 berarti valid deh. Tuh. Nomenclature. C C2 is from the table 1. How about Figure 5. Check. So what? See, for the process oxygen integration. For the oxygen integration, it refers to figure 3, just on the description. The discharge, both the discharge from process 1 process 2, so based on the description, the process, the discharge from process 1, process 2 will be used to combustion wastewater treatment. This information is limited. First, oxygen is 30 per without the cascade analysis, it's 41 kg per second. So from the 30 kg per second, 143 goes to process 1. Here it's 10%, 10 kg per second. Outlet 3%. Some goes back to be recycled 2.57 kg per second. The rest goes to other, like 1.43 goes to process 2. Since there is no happens condition, condition means Of process one, process two, what is the range of the concentration that allow. Without that information, then we don't know which one goes to which one. You see here, 40%, meaning the feed here is mixed with 20% of 3.5 liters of water plus 21 liters of 5%. Next is the process two. Process two is similar, 40% plus 5%, 5%. Not 45%. It will be diluted after process two. There should be this to 50% goes to the wastewater treatment plant. Some goes to the discharge 1 kg per second from process two. For wastewater treatment, another 1 kg per second is coming from process one. For combustion, it's supplied by process one. Okay. Okay. Screen condition given. Let the page two, right? Papers. Capital revenue above and below page. For this question, value above the pages. Go back to this the cascade level. So, the nitrogen integration value above and below the page is FC is at 75, 0.125, 65. The one is a good with concentration of 0.2 and 0.1. Because the pitch occurs 8.4, below the pitch is more. What is more than nitrogen? 4. Figure 5 is the same. Let's see for figure. One has it. Hydrogen integration. Since hydrogen is a valuable liquid gas in crude oil refineries and petrochemical plants, hydrogen reuse and recycle has been subject to extensive research. This is refer to example 3 paper. Figure 6 shows hydrogen network study. The existing hydrogen fresh hydrogen production is recorded at 2775 mole per second here. Figure 6. There are 4 hydrogen consuming process in this case study, which is hydrocracker unit. You have naphtha hydrotreater NHT, crack naphtha hydrotreater CNHT, diesel hydrotreater DHT. RU ya Pak. There are 2 hydrogen processing facilities in this network, catalytic reforming unit, CRU, and state reforming units, SRU. These are the internal hydrogen sources for the network, and their use is to be maximized before considering the purchase of hydrogen. So fresh hydrogen supply having 5% seven for this case study. So there are 3 sources of hydrogen in this case. SRU, CRU, import. So import is the purest at 5%. One is 2772 mole for SRU 623.8 for the second. CPU is 415. So meaning SRU, CRU, and import here is the gas source as well. 6. Limiting data for all hydrogen sources. 10.6. Note that the limiting data for the hydrogen network cannot be directly extracted from the process for diagram such as step figure 6. The detail considered to extract the limiting data is presented as yeah. So for the guessing, it's a HCU. So remember, guessing is equal to gas demand. So meaning the stream is entering the processor. For the process, there are 4 only: HCU, NHT, CNHT, and BHT. Meanwhile, for the gas source, 6, including the supply. So from each of the sink, you will produce the gas source as well. HCU doing the stream coming out of the HCU, HT, CNHD, DH. The other two sources is from the SRU and CNU. So for this is for the case of hydrogen. Still remember the case for the Sultan almost yesterday. There's a rainwater harvesting. So the rainwater harvesting is considered one source, water source for the case for the process. Similar to this. So these two units produce the hydrogen. Using steam or what is the one? Catalytic forming. So to do this, it's a lot. I'm not sure how many. there are there are 11 level based on the concentration. You see the concentration for the lead acid very specific in 29%, 120. That obviously I showed in turbo 7, turbo 7 shows pressure, hydrogen target at 68 mole per second with discharge flow rate is 200. The density unifies CNHD. CNHD is 30%. Unify the CNHD as the pinch causing string from which 354.879 or 88 mole per second must be sent to the region above the pinch, and 102.552 mole per second must be sent to the region below the pinch. Further reduce the oriented means to the wow, very far. Very well. So in order to do this, we need to start with concept from zero, identify the largest negative, the highest value with negative value, then choose that value for the fresh feed, fresh flow rate, then redo again the cascade table, make sure point that you choose for the FF, turn to 0, this is pinch, any value above 54, 79 will become the of the pinch. Meanwhile, this value below the pinch is still below the pinch. So hydrogen. So in order to reuse again, gas or to further reduce the fresh oxygen intake. It can also treat it, let's see, hydrogen purifier to improve, to increase the purity, the hydrogen from the source. Hydrogen purifier manipulate the properties of hydrogen stream to match the desired hydrogen stream. What else? Oh, okay. The common hydrogen purifier include pressure swing absorption, PSA, thermal separation, hydrogen separation. So each of the method to purify the hydrogen will have this limitation on how pure the hydrogen it can be treated. The hydrogen purification unit typically separate single hydrogen stream into product stream one. Okay. Two.
Hi, doctor.
Yeah.
We have another class that is starting right now at 2 p.m., which is class
Oh, is
with
it?
with Dr. Ruby.
Oh. Okay. Is this a master class as well?
Sorry, doctor.
Is it a master class as well?
Yeah, master class.
Oh, okay. Then we don't have any appointment. Sorry, any class after this. Okay. There are a few others actually that I need to cover. It's okay. I just do the recording. Later you just follow from there. Okay.
Okay, all right.
Wait. So somewhat. Anyone here haven't take the attendance? Let me share first. Got the attendance? Yeah, I need to continue. Okay. Yeah, you can join that class and finish.
Okay, thank you, doctor.
Yeah, thank you, doctor.
Finish. So each of the hydrogen purifier have its limitation. You see after this. Even a gas separation, or this is starting with the membrane, and membrane. With a hydrogen recovery of 95%, which is pretty high. One possible option is to purify the portion of the finished constant stream, which is CNHP, the last below the pitch at 30%.
Doctor, can you share
One
the
or two.
slide?
Yes, yes. I will share
You are
the
still
slide.
sharing the
slide.
attendance.
Oh, is it? Oh, okay. Oh, thank you.
Okay, okay.
Thank you. All right. You may join Prof. Ruby. It's okay.
No, I'm not taking
Finish up.
that class this semester.
Oh, you're not taking the class. Oh, that's
No.
good. Someone here. All right. So for this, we start with membrane. There are two countries. So there are two others, membrane and PSA. So we see the difference. So for this pinch causing stream that lies below the pinch at 2%, 102.52. So 102.52, if you refer to table 7, one is below the pinch. If you still remember for the water, one of the guideline is do not treat the water so that purity is more than the, sorry, start again. Do not treat the region below the pinch so that the purity is above the pinch. This is different for the gas. If you do that for water, one thing is it will consume a lot more fresh water for that process. So for water, if the region is below the pinch, if you want to treat it, then you treat the purity must be below the pinch. If it's above the pinch, that one is it's okay. Depend. But for the gas, it's different. For the gas, we treated the below the pinch to a stream product stream quantity at 2%, which is very high for me. 2% is better than the fit itself. Sorry, the import stream. The import stream for this example, 5%. Refer back to figure 6. So after you done the treatment, they didn't specify. Yeah. No, they didn't specify. They just specify the percentage of it. Blah blah blah. Okay. Only 69. No? Should have this. Then I guess we should have the V. Oh, no, you have to say this one. Sun February. Sun. Ay, balik ka pa. Tidak betul sila. Okay. Do the in this person. Explain again. You see here 95% average. Since this the FD from the hydrogen integration is around 102. Wow. So 95% of 35% something is around 96 point 6.9. But here the value is jump the value 69.6. Just okay. Scale that. 8%. Percent. 64, 65. Percent. Oh ya ya. Faham dah. Okay. Relating the oh. So this is the material valence calculation here is referring to the membrane. When we treated the FD from table 7, is actually the permit meaning the amount of treated hydrogen gas after passing through the membrane is only 69.57 mole per second. Is this one. And the fluoride impurity ignition for the concentrated retented strain are 32.95 to 69.57 plus 32.95. It's 102.52, which is if you add up these two values, 32.95 and 69.57 is actually similar to FD in table 7. And the concentration for the retented means the gas, because the membrane of, in this case, the membrane is a cross flow membrane. So the gas that is not treated will be just pass through those being treated will pass through the membrane. It is so there's a flow of gas. Some of it goes straight to the membrane. Some of it goes pass through. So the pass through across the membrane, we call that one is rotated stream. The percentage, the concentration is around 89.11%, which is very high. This is a problem with the membrane. Although you get very clean concentration, but you will be left with a very concentrated stream. Okay. So after that, since we have two additional stream, from the additional stream, we create another table. This is for the case with regeneration. So meaning you have three at least gas cascade table, starting from the FF of 0. Then we identify the pinch using that minimum gas flow rate as the fresh feed. We do again the GCT. From there, we can get the discharge flow rate. If we were to regenerate, in this case, we generate the below the pinch. So from the regeneration, there are another two concentration level after the treatment and the gas that cannot be treated, that has not been treated. So it will be part of the concentration. They need to redo again. But in this case, the 2% after the regeneration is higher than the FF itself. FF is at 196.8. Two, 6. Yes. 6.3. So another question. For this case, does the FF start with 0 or not? Since we don't know the pinch now, I believe the correct answer is we start with 0 again, just to identify the pinch, meaning the FF here is at concentration level 2, 5%. Concentration level 2, concentration level 1, we have the value. This one is based on this statement. But for 5%, which is the feed or the import, we don't have the value because if you still remember,
Doctor,
for yes,
why the first FC is not 96.6? The first FC.
Oh, the 96.6 is, that one is my mistake. Because I assumed that 95% from the 102.521 will be recovered based on this first statement, which is not. They come up with another statement here, the second point, which is saying that for the membrane treatment, only 69.57 being treated to this quality. The rest is becoming the waste from the membrane. So that waste is account 32.95 mole per second with the concentration around 99.11%. So which is why 69.6 is for the fit for the 2%.
So how
So
they
the
get
debate
this one?
now, this one?
96.57? How they get the 96.57? It's from the
Which one?
statement. 96.57, the first FC.
I don't think they said 96.57.
No,
69, right?
69.57. Yeah, the first FC is 69.57. It's not the same like the first one, 96.6. So they got different
Alright.
there.
Yes, correct. 96.6 is not correct.
Oh,
The
that's
one I assume 95% recovery, which is wrong because I
so.
didn't read the second statement.
So supposedly at the 96.6 is what?
There is no 96.6.
But in the table got there. In the table
Where?
ada. Nanti ya, ni kita bulatkan merah ya.
Oh, the one is 69.6.
69.6. Oh.
Yeah. Wait, so this value is the same as this value.
Oh ya, betul.
Round often. There are no 96.6. Oh, macam sudah. So with the generation, yes, should start with 0 first, meaning the fresh supply is to be determined. That one is referring to table 6. The fresh supply to be determined. Since we have a new 2 new stream now, so FF start with 0, find the pinch, then start again another gas cascade table calculation using the pinch. The highest negative is around negative 1.96.8. Then determine again the pinch. So from here, we identify that the fresh heat required is really is reduced by about percent. For the gas cascade itself, without the regeneration, it's require around 268.8 to 1 mole per second. After the regeneration with membrane, only require 196.8 mole per second. Even the discharge is really low without regeneration. It's around 30 right? Previously it's 102.5. Let's see if we, 102.5. 102.5. we use PSA, pressure swing absorption. So pressure swing absorption is more expensive compared to membrane separation because it require at least 3 absorber. The principle of it. Let us assess another hydrogen prepared PSA unit with the hydrogen recovery value of 90%. This is lower than the membrane, but the purity of the hydrogen is up to 10.1%, which is very, very good compared to membrane. From material balance calculation, one obtained the product residue flow rate of 64.65 mole per second and 37.87. This is the residue, this is the product. With the residue stream purity concentration of 81.05%. So there are two new stream. The first one is 0.1, the product. This product is from PSA, from the hydrogen purifier, around 64.7 mole per second. Another one is reduced at 1.05 strength. So similar, you start with FF is equal to 0. Identify the pinch. So pinch here is at negative 200. If you do FF equal to 0, then using the 200 as the minimum gas flow rate, minimum fresh gas flow rate, then you do another GCP. So here, berapa tadi? 196. Oh, this one is 200. So for the fresh hydrogen feed required is around 200 compared to the membrane is 196.8. The discharge is around 33.711 compared to membrane is 15.475. Okay. Note that in this case, the PSA has also purified the hydrogen source to a higher level relative to the fresh hydrogen supply. We can now conclude that gas separation membrane plays a more important role in reducing the fresh hydrogen target of this hydrogen network. Compared to the PSA, it is due to the fact that membrane is the higher recovery 95%, recovery of 90% generate an additional amount of hydrogen from the region of excess. Below the PSA region of hydrogen deficit. However, one should note that a purifier that gives a higher recovery may not necessarily be better. A purifier that produce a product stream at higher purity, PSA in this case may sometimes be better solution in using the we will examine this solution in the finish product position. Multiple pitch problem. This is hydrogen. Oh, see someone. Table 10 shows the hydrogen source in sync data. There are 6 hydrogen sink and 7 hydrogen source in this network. The fresh hydrogen supply in this case has a rate potential of only 1%. Using GCA, the minimum fresh supply is transported found to be 1 to 5 centimeters 1 mole per second. 2.96 moles per second in table 11. Okay. So for this case, just a moment. 1, 1.5, 3, 10. Okay, this is on. Okay. So table 11 shows 2 pinch. Pinch. Table 3, 7. Situation level 3 and situation level 7. The 2 pinch observed in this GCT with the position of 1.7 and 5%. 7, 3. Okay. Following the terminology in the water network, the pinch concentration at the lower impurity concentration of 1.7% is designated as the limiting pinch. This pinch that influence the overall gas flow rate when any process changes take place. One. So to be repeated. In problem involving multiple pinch, more than 2 design regions may exist. Example 4, 3 distinct regions exist due to existing of a limiting pinch at 1.7 and secondary pinch at 5%. Utilizing the GCA technique, one can quickly identify the pinch volume stream and the exact hydrogen location for the hydrogen source in each of the design region. This can then be verified using the network design for the procedure described previously. One of the possible network that achieve the established network target is shown in the picture same way. The correct animation of the meeting page is to show in problem involving multiple pinch point near pinches. So based on this, the 3 region. There are region above the limiting pinch, region below the limiting pinch, region below the secondary pinch. Identification of the wrong pinch point will result in missed opportunity during hydrogen network debottlenecking. This is particularly important for a problem involving multiple pinches. Where the region above the limiting pinch is the most constrained part of the network. Debottlenecking strategy will only be beneficial when the hydrogen source flow rate is increased above the limiting pinch. Okay. Alternatively, decreasing the need of hydrogen sink in region above the limiting pinch will also achieve the debottlenecking objective. This is another area where quick and accurate relation the true pinch point and target distribution on gas process. Here once again this area is play. So for this case, I need it right now. Based on this, it's rated below the pinch. Okay. Given the same hydrogen profile in example 3, we can now determine the appropriate selection of purifier that will reduce the overall hydrogen product of the network GCT for purifying the hydrogen source using a gas separation membrane. Okay, it can be 95%, please implement with 2% to ensure that the level smooth. 70%. Hydrogen or 0.1% here. Okay. Thank you. But below, before the 2%, there are the stream which is better than the membrane. Note that though the secondary strip accent has been removed, the minimum flow rate target for this option are the same as before regeneration. It doesn't say which stream, but assuming since this is the limiting pinch, then we just choose below the pinch, which is 97.41 mole per second to be treated above the pinch. Let us see. Niat ang pintuan. Tidak saya besok dulu. Still, no. Tiga, tiga, empat, lima, sepuluh, 15, 17, Good. Huh. See the last. For this two stream, I'm not sure which one. Because we know the pinch. 27.41 per second. But based on this table, we add up these two. It's actually 120. 120. So, finally, 6. Beliknya. Okay, but oh, this two value is coming from the here. What? True. But after the verification, even they didn't tell info how much is treated. Based on this, we can see 1 of 4.69 in cremated or treated to 2%. Meanwhile, 15.31 is the treated is at 64.72%. Then redo again. When oh, 0.1%. So FF is 0.1%, meaning it's the highest lah, ke atas. So start with 0 first. Since we have two new stream now, then calculate, identify the pinch, negative 1 to 521 from here, you can use that value as the new flash flow rate, flash gas flow rate. We calculate, identify the pinch. Okay, that one is for the so once we use membrane, then there are no secondary pinch. How about use PSA? By using PSA, the purity is 0.1% compared to example 3. The hydrogen percent resulting still strain at 2.42%. The residue of 52.71%. Divided the product wise. Tadi pasal B1 memang pusing. B1 dan please tadi 120 120 plus this is product from the PSA, this is the residue. Similar, start with 0, identify the pinch. 0, identify the pinch. Then using the pinch to recalculate back to speed, identify the discharge. Now, we refer to membrane. The amount of fresh hydrogen required is 125. With discharge is 90.96 per second. But using PSA, although the recovery is around 20% with concentration of 0.1, which is better, much better, you can reduce the fresh hydrogen target by half, 4.23%. And the discharge is very, very low, 20 mole per second. Even the pinch is level 10. Because of the reallocation of hydrogen source within the whole network, the original limiting pinches disappear. When a new pinch emerges at the residue stream within 50%, hence within the PSA plays a more important role in producing the hydrogen this network. As a question rate. Applying the resource hydrogen in the pinch. Industries apply extra nitrogen, hydrogen, what's the pH? Anything pH? What measurement? Oh, good lah.
Doctor,
You know the yes,
how to get the delta M?
delta M.
Yeah.
What?
Yeah, this one. Yeah.
Okay. For the delta M, itu dah dapat. Ini ada dalam paper. 1, 2, 3, 4, 6, 7.
Dalam
Betul.
kitab tadi,
Dalam paper aja.
dalam paper, dalam soalan tadi lah.
5, 9, 8, 8. It's similar to example 1, example 2. But example 1, if you refer example 1, it's explained in detail. So for the delta M, which is impurity load, it's a product of community gas chloride FC and the concentration different across two concentration level delta C. So delta M here is equal to FC multiplied by
Concentration.
C2 minus C1 ataupun 1.4 minus 0.1. That's what here. So 1.4 so 1 bahagi 100
Concentration 1.4 minus
0.4 watt. Actually 0.40989 yeah, the run off jadi 0.4 watt.
and then multiply by
Multiply by difference between level lah. For this case,
yes.
is C2 minus C1. Let's say
C2.
for here 0.11, it's actually the C is C3 minus C2. Dia macam water, but for concentration, water is simply for gas is using concentration.
Macam ni tadi? C2 minus C1.
Okay, for so for this,
Yeah, for the first
one, it's actually a multiplication of FC
FC.
with C2 minus C1.
C2 minus C1.
Let's say this one. Level 6. So for delta M, C level 6 FC multiplied by 4 minus 3.
Kenapa Messi dapat tak?
Dah bagi 100.
Oh, bagi 100.
Because this one is in more percent.
Oh, okay,
Yeah.
dah bagi 100. Okay.
1%.
Okay,
So bagi 100 lah.
Lepas bagi 100 dapat lah.
For water doesn't have to divide by 100 because the way it's calculated is different. For gas, yes, you need to divide by 100.
Oh, okay. Dapat lah.
Conclusion, I guess the cascade is tool for developing the minimum flow rate to water in previous Yes, cascade we see TC enable quick infrared with pressure and minimum flow rate is from different you get it. Filtration again to generate candidates with this all for me. For the final exam, focus on water and cascade analysis. Any question?
Tak ada.
Thank you. buat example exercise
Mm-mm.
ya.